Okay, we're ready to get started into Chapter 4. And hopefully after today's lecture, things with regards to sampling theory, things that showed up on the very first lab problem with the chirp, remember the alias chirp in the handout that I gave out in the lab on Friday? Hopefully some of the math behind that now will start to fall more into place as we continue to go through this week. There is a new assignment sheet up, just so you know that's there, and it's due on Monday the 5th. In case I don't get a chance to get into it more, the very first problem on this assignment sheet is a carryover from the end of last chapter, and it's just giving you the opportunity, like I had said, to practice at working a little bit more with Fourier series and just doing some plotting. So here's a piecewise description of a function. Another opportunity to find a Fourier coefficient A0. This is that parabolic shaped function. You'll sketch it out in, well, if you look at that definition, maybe you can already see what's going on there, but you'll sketch out this function and then find its A0 coefficient, and then I'm giving you pre-computed that the Fourier coefficient is what's down below here. This guy down here, and then you can go in and plot the approximation to that waveform using the synthesis plotting that we talked about last week, and there's a couple of examples of that in the notes. Remember, one was to reconstruct the square wave, the other was to reconstruct the triangle wave. So this just gives you some other hands-on with MATLAB and giving you a chance to play around with Fourier series a little bit. The rest of the problems will be on sampling theory, which is what we're talking about right now. So we started on this last week, and I didn't plug my power supply in yet, so guess what? If I take chances, my battery will go dead. So one of the things we're going to be getting into in this chapter is this is the gateway to digital signal processing, which is what we're going to be doing pretty much the rest of the whole course. We'll be doing the digital signal processing side of the introduction to signals and systems. So what we have to have if we're going to be doing digital signal processing, we have to have a means of getting from the analog world and then back out to the analog world. So we're going to, at this point, talk a little bit about these two boxes that the book defines as continuous to discrete and discrete to continuous. And I'll say more about that in a second. And then this chapter also, of course, has the sampling theory, and the low-pass sampling theorem is one of the fundamental results that comes out of here, how that works and how we go from continuous to discrete and then back again, actually proving that and letting you see how that works. Most everybody believes in it because that's how you listen to digital audio when you listen to your music player. It's come from a digital format back to the analog domain, but what are some of the particulars of that? So we've been dealing so far with continuous time signals, except for the introductory material, so some function of the independent variable t. Now we're going to be switching gears and we're going to be dealing with a discrete time signal x of n, which in most all instances for us is going to just be a sampled version of the underlying analog signal. So it'd be like what the computer is presently doing with my speech. It's sampling it and storing it into a record along with the screen video. So we had a cosine omega t plus phi, which we've been playing around with a lot extensively. Now we're going to be switching gears by sampling that waveform. We're going to be replacing t by n times t sub s, where t sub s is the sample spacing. So we'll get our sequence as we go through our continuous to discrete converter. We'll get our output sequence x of n, and it will be as a result of sampling with a spacing of ts, or at rate 1 over that, which would be fs, number of samples per second. The book has this abstraction called the continuous to discrete converter, and the mathematical model for the ideal continuous to discrete converter is simply a switch, something that can take an instantaneous sample every t sub s seconds. But engineers build things, so is that going to be good enough in general? I mean, in this class it'll be good enough, but we have to be able to go beyond that. So that the name that's used from the hardware domain would be analog to digital converter, or the other terminologies, abbreviations would be A to D, or sometimes spelled out as ADC. And I'm willing to bet everyone's heard that terminology before, A to D or ADC, at least one of those two terms. Is that true? So there's different technologies that are used to actually represent, to implement, an A to D converter. In all cases, we get a finite number of bits of precision, so we may have 16 bits, 18 bits, 12 bits, 24, and so on. Intuition would say what about the number of bits per sample? What's good about having more bits per sample? What's not good about having more bits per sample? More memory needed. If you're sampling at, say, 44.1 kilosamples per second, which is the CD standard, and you're sampling at 16 bits per sample, then the amount of memory piles up in a hurry. If you could cut it down to less samples, that would be nice. But what's the disadvantage of not having enough samples per bit? Or not enough bits per sample, excuse me. Not aliasing, but fidelity. We have more error, so we have what's called quantization noise that creeps in the background. A 16-bit converter, it's not a subject of this class, but a 16-bit converter will give us a signal to quantization noise ratio of around 95 dB or so. Most of us can't hear that dynamic range all that well because 90 dB is a lot of dynamic range. I don't know if you remember the spectrum analyzer demo on Friday, but that display had graticule lines on it, and the total number of graticule lines from top to bottom, I think, is about 8. So I had it set in a mode that was displaying about 80 dB of dynamic range, and remember all the fuzzy stuff that was down there, and the spectral lines were just above it. There wasn't that much dynamic range displayed in that demo, but that was not intended to be as high a dynamic range as, say, an high-quality audio application would be. Okay, does anybody know what SAR stands for? I guess I wrote it out, Successive Approximation Register. How about flash? Flash is a type of memory, but in the A to D converter business, what flash means is that you can have a comparator for every bit in the conversion process, or every quantization level. So if you were doing a 10-bit converter, there's 2 to the 10th quantization levels. So that's 1024 comparators that are needed so that you can instantly, as soon as the sample hits the front of the converter, you hit it with a clock and you say, what is this analog sample convert to in bits? You have to have a threshold for every power of 2, or every 2 to the n that you've got in your converter. So that's a lot of comparators, a lot of hardware. But if you need to do things quickly and you want the precision, the flash converter is the ultimate. The delta sigma is a technique that's very popular in commercial audio systems like music players for playback, which is the opposite of the A to D. So what is the opposite of the A to D? Since I'm not going to mention it here, if you have an analog to digital, what's the opposite? Yeah, so that's DAC as opposed to ADC, and D to A as opposed to A to D. The technologies are similar on the way back, but they're hooked up in a different fashion. So the delta sigma is what's the most popular, and it works by oversampling, and then it uses digital signal processing inside the A to D to actually get more bits of precision. So what's possible with the delta sigma is to sample at the front end with only 1 bit of resolution using a single comparator, but then through the oversampling and the filtering that goes on, once it gets into the discrete time domain, you can get additional bits of resolution by oversampling. And a way of thinking about how that's even possible is that if you take a lot of samples of a signal and you average them, you can get an additional resolution performance improvement. Just think of, numbers being measured somewhere or another with small amounts of error. When you average a bunch of numbers, what happens to the error, hopefully, if they're independent measurements? You can reduce the error down, right? So delta sigma tends to work that way, and it's the newer technology. It's not something that can operate at really high conversion rates because you have to oversample. You might oversample at 64 times oversampling. So in an audio bandwidth, you can handle that 64 times oversampling, but if you're working in a radio receiver front end, the 64x oversampling is going to put you into the gigasamples, and that's going to require very powerful post-processing. It's going to use a lot of current, and so on. Well, I'm going to pass around 2 things. I guess I'm going to ask a question. If somebody could come up here and get this as soon as I'm ready to pass it around. How many of you as electrical engineers like hardware? No one will admit they like hardware? Okay. How many of you think maybe you're going to like hardware someday? Okay. Digital signal processing, if you look at the courses that I'm teaching and the courses I typically teach, one of the classes I'm teaching right now is real-time digital signal processing, and that uses dedicated DSP hardware boards. And these are 2 of the boards that I'm using in the class. This one is a bigger board that has more memory and a daughter card, and it has a nice audio band, A to D and D to A in stereo, so it's got the stereo jacks on it, which you can clearly see are line in, line out, headphone out, and microphone in. This is a TI C67 13 DSP microprocessor, and it programs with a code programming environment called Code Composer Studio, which is the same environment that can program the class that the processors, the microcontrollers that are used in what's the course number? 200 something. 3420, and also isn't there? Okay. It starts as 2000 something, doesn't it? First one. Whatever those classes are, I was involved with that MSP 430 changeover, but so that's this guy. And then just to show you that you can get them smaller and cheaper, here's a little tiny one called an Easy DSP USB stick, and this has a fixed point processor on it, but it has a line in and a line out, so it has a stereo codec on it, and the DSP processor, and it plugs right into the USB. This board here is $395. This one's $50. The reason why I asked if you liked hardware, you'll appreciate seeing the boards. Don't zap them. This one is sealed up, and I want you to keep it sealed up. You can just see how small and kind of cute it is to be able to carry it around. I take the little one home with me when I'm working on the class stuff. I can plug it in. I did a demo in class for those guys last week. I pulled out my iPhone and plugged it in as an audio source because I have a couple different function generators on here as phone apps, so they generate sine, square, and triangle and noise sequences. So I used it as a test generator, drove it in there, and then we could listen to it on the headphones. So by the time you guys get a little bit further along, you might be interested in, there might be even better development kits out there than these already.
Does this connect to a PCI slot or a computer?
No, that goes right in the USB. See the USB?
The connection at the bottom there?
On the edge?
Yeah.
That's a custom expansion port connector. I had some students last spring in the real-time class basically interface that out to a modem so they could pull data in and out to a PC for the graphical display. Those of you that are into embedded systems already, and most of you are not, but most of the new embedded systems kits have the capability through the USB interface to have a modem running in the background, a serial modem, so you can actually upload and download data streams besides having the USB do its job. That particular board does not have that capability, so you have to use that expansion socket on there. The big board has other high power, high performance debugging interfaces built right onto it. But basically we use the USB for the debugging and downloading code and so on. But one of the neat things about both of those boards is that it's not just the digital world, it's the analog world that you interface it to. So we use the instrument that I had in lab last Friday, the spectrum and network analyzer, to characterize the performance of the DSP algorithms running from the analog perspective. And in the next chapter here, we're going to start on digital filters. We'll be looking at the first type of digital filter after we get through sampling theory. Since I got into electrical engineering at a young age, I wasn't an engineer at a young age, but I got interested in electronics when I was in junior high and then in high school. Did a lot of building. Everything hands-on is what kept me interested in continuing my study. And these days, I think it's harder, so you have to come up with an angle, and some of these development kits, I think, could be your angle. After you've had this class, you could come and take real-time DSP as an elective class eventually. I wouldn't suggest taking it as a junior, but as a senior, you could take it. Okay, how do we represent discrete time signals? Well, MATLAB has a special plotting function called the stem function. So we use stem instead of plot when we want to plot a sequence. Most people call it stem, but in the early days of my teaching this, it was also called a lollipop plot, which sounds kind of cutesy. It's because they look like little lollipops with long sticks, I guess. Can anybody see that, or does that sound kind of far-fetched? The idea, though, and this is a big deal, is that if it's a sequence, does it have values in between the integer values of its independent variable? In other words, could I have a sequence value at 4.5? I can't, because I'm sampling at integer time ticks. Every t sub s seconds, I take another sample, so there's no... The analog waveform has a value in there, but the sequence only is evaluated at integer time ticks. So we're abstracted now when we go to the discrete time domain to sequences, and you can actually teach digital signal processing entirely from the sequence point of view, not visualizing that it might have come by sampling an analog signal. In this class, we don't take that view because it's a little bit too abstract. I'm thinking, if I was you, I'd say, let's get real. We're engineers, we're not mathematicians. We want to know how these sequences come into being. They come about because we sample in the continuous time domain and get them into the computer to work with them, and then either ship them back out, reconstruct it as analog signals again, or just work with them as sequences and maybe do calculations and analysis to pop up displays, make decisions, and so on. And a good case in point might be in a car. at one time, I think the speed control was probably all done in an analog fashion. I think today it's done in the discrete time domain where the signal values are sampled with some microcontroller or DSP on board the car, and then it's a sequence, and then there's filtering done, and then there's an algorithm that brings in data from the stick on the steering wheel where you set points. You press the accelerator, you bring the car up to speed, you press a button, then that locks the speed you want to drive at. So that's likely digitized into a threshold value that then the speed of the vehicle gets compared against after it's been digitized, and then it's just a digital control algorithm that just steps effectively the accelerator up and down to keep the speed regulated at a given velocity. And then, of course, there's all the safety mechanisms that are in there, so that if you hit the brake, hit the clutch, if the accelerometer in the vehicle is tripped, it will disengage. Speaking of algorithms, I also worked one time for Ford Microelectronics when they used to be here in town, and got a chance to understand a little bit about how the accelerometer on a vehicle is set up. Don't know the proprietary part of it, but the accelerometer is part of the main key in deciding if the airbags are going to blow or not. So there's got to be some very significant decision making done based on the waveform that gets sensed by that accelerometer, and it's done as a digital filter and then processed and compared against a threshold. And the way they explained it to me was they spend a lot of time getting it right, and how do you suppose they have to get it right? They have to test it right, ultimately. So they have to crash cars in order to really know that it's working. And that's fairly expensive to keep crashing a lot of cars, so they do a lot of simulation, but eventually they do have to test. So I asked that question, how many cars do you crash? And they just said we try to avoid crashing too many, but as consumers, we hope that they test enough so that it does its job. So you'll be using the stem function, and the stem function is also, I didn't point out here, has got a few options in it. These are options that a lot of times you won't use. You can have it be filled. If you don't fill it, you just get an open lollipop. You can set the color. This was set the color to blue. And then you can set the thickness. This one you'd rarely use, make it be a fatter stick, and I just did that for this plot so that it would show up better. So most of the time you'll just use the first two arguments, the x-axis n and the y-axis signal values, which were stored in x. Okay, now things are going to get a little bit interesting compared to what your comfort has been. We're going to look at sampling sinusoids. So we're going to have a sinusoid where we're going to replace t by n times ts. So it looks pretty benign. We have omega times nts in place of omega t. And now the book defines a new variable, which is a little bit of a pain to have to write, but you have to put a hat on top of it. And the hatted variable omega is omega times ts, or omega over fs. And this is called the discrete time frequency, or normalized continuous time frequency. So when the hat is on top of it, it's normalized by the sampling rate. So technically, if omega was radians per second, which is 2 pi times cycles per second, and you divide by cycles per second, what does that give for the units of omega hat? Just plain radians, which is kind of misleading. So some books will say it's radians per sample, where samples are dimensionless, just to emphasize the fact that it's implying that sampling is involved. But technically, from a math standpoint, the units are purely radians. just kind of a weird thing, since most of you don't do typesetting or have to use different languages like I might use for writing my notes. The hat has also got a name. It's not just called hat. That's the convenient name for it. Does anybody know what the more specific name is? I'm just curious. I had an advisor that was particular about things, so that's when I learned the name. It's called a circumflex. Has anybody ever heard that term before? Pardon me? Okay. Call it hat. It sounds more polite anyway. Circumflex sounds just kind of bizarre to me. Okay, we can also define a normalized frequency as opposed to a frequency in cycles as opposed to radians per sample, and that would just be normalizing f in hertz by the sampling rate. So that would be f hat is f over fs, and then that would have units of cycles per sample. So let's take an example and start seeing what goes on here. We've got a 60 hertz sinusoid. We're going to sample it at either 240 samples per second or 1,000 samples per second. So with the 240, the sample spacing is 4.1666, etc. milliseconds per sample. And with the 1,000 hertz sampling rate, the spacing is 1 millisecond. So I just wrote out some MATLAB code, and here are the three waveforms. And the continuous, where I use the plot function so that I connect the dots, and then I use the stem function for the second two. So this is appropriate to plot the continuous using plot so that the actual values are connected in MATLAB, and then stem emphasizes the fact that we only have the values where the samples have been taken. Both of those are valid discrete time sinusoids. It's just that one's been sampled at a higher rate, so it looks a little bit neater. But based on what we were talking about last Friday, if the signal is at 60 hertz, some of you noticed when you read through the lab that the sampling theorem was quoted, and you were echoing that back to me when I came around for sign-offs and stuff. Some of you remember what that sampling theorem said? We're going to get to it here in a bit, but does anybody remember?
Something about aliasing in periods of 2 pi or something.
Okay, that's another part of it, but what was written in the lab manual? The sampling theorem says that you need to sample at greater than twice the highest frequency. So in this case, with the 60 hertz sinusoid, if we want to avoid aliasing, we have to sample at greater than 120. So sampling at 240 is adequate. You might look at that picture, though, and say 4 samples per period. That seems kind of not too good. Can we really get away with that? And it turns out, with the sampling theorem and so on, yes, we can. We can reconstruct the 60 hertz sinusoid perfectly, to within an epsilon, let's say, with only 4 samples per cycle like that. And that's something that initially seems kind of unbelievable because we're used to drawing pictures, and a few weeks back I was talking about plotting sinusoids, and remember we discussed how many samples per period would make the picture look good. I think we concluded that 10 was kind of coarse looking, 50, maybe even up to 100, no problem because MATLAB can handle it. But when we talk about sequences and actually wanting to consider sampling theory, we don't need to be in the business of overkilling, because that just means that we have more samples per second to process, and the computer, the embedded system that's going to work on it, is going to have to work harder. The little tiny DSP board I passed around clocks at 100 megahertz, and the bigger one, that one is quite a few years old, but we still use it here. It clocks at 225 megahertz. But the processors on there, on the big board, just as an example, have quite a bit of parallelism. It's a floating point processor on the bigger board, and it can do 2 floating point multiplies and 2 floating point adds per clock cycle. So it has quite a bit of throughput capability with that architecture. So if we go through and just calculate out what are the normalized digital frequencies in terms of omega hat, we have, when dividing by the sampling frequencies, we get 2 pi times 0.25 and 0.06 times 2 pi. So if we were then to take and convert those to sequences, we'd just be plugging those values in as arguments. And we'd say we now have a sequence, a sinusoidal sequence, rather than a sinusoidal signal. Sequence because it's indexed on the integer's independent variable n. And we'll get to the reconstruction here later in this chapter, but we'll be able to perfectly reconstruct the original signal to within an epsilon, like I said, given those values. Now you're probably thinking, based on last week's lab, there's got to be a limit, and how does all this stuff work out with the aliasing? So that's what we're going to move on to next. So the concept of aliasing, we talked about this briefly last Wednesday, and we looked in the dictionary definition, and we came down to this third piece, the telecommunications portion, is what we're doing here. When sampled at a given uniform rate, would give the same set of sampled values and thus might be incorrectly substituted for another. So that's what we're going to be looking at initially, and it's kind of perplexing, but it's just a property of the cosine function and the way the sampling theory is going to work. So we take 0.4 pi n as an example, so omega hat is 0.4 pi, and we know that cosine is a mod 2 pi function, so what about 2.4 pi? Well, when we break that down, we have a 2 plus a 0.4 that can be separated apart, and then when we multiply that through, we have the original 0.4 pi, and then what does having 2 pi n do in the argument of the cosine? Does it do anything? It doesn't do anything, right? Because cosine's a mod 2 pi function, so that 2 pi n is transparent to the way the function evaluates because it's a mod 2 pi function. So now we're seeing that, oh, it's not unique to have 0.4 pi to get samples, to get a cosine sequence. We could have 2.4 pi and we get the identically same samples. So these guys are identically the same sequence. So that's one pair of frequencies that alias to each other. So in general, any 2 pi multiple of some value omega naught hat, and it got clipped off here, will produce the identically same sequence. And that's just due to the mod 2 pi property. Then furthermore, since cosine is an even function, in other words, cosine of pi is equal to cosine minus pi, we can actually do a difference here. In other words, 1.6 pi could be written as 2 minus 0.4 pi. So that would factor down as to saying, now we have another 2 pi factor that is irrelevant, and then we have a minus 0.4 pi, which due to the evenness, again, would take us back to 0.4 pi. So in reality, what we're saying is that we can take some original omega naught hat, and we can add or subtract multiples of k times 2 pi, and just take the absolute value so we get positive numbers, and all of those frequencies are valid. I mean, they all give the same sequence, is what I'm saying. So 1.6 pi, 0.4 pi, 2.4 pi. So if you want to write it in terms of positive numbers, you can do it where you put the 2 pi L first, And if you're doing the difference, you put the 2 pi L first, subtracting omega naught, or if you're doing it with the sum, you can put it second, so omega naught plus 2 pi L. They all give the same signal in terms of cosines. If we were dealing with sines, the sine function, then there'd be a numeric sine value in the samples just because sine is an odd function. Since sine of minus theta is equal to minus sine of theta. The values would be, to within a sign difference, would be identical, but they'd just be flipped. So in actuality, that still makes it the case for aliasing, and that I kind of have to work through with you here in a bit. This equation 411 is one way of expanding it out to handle any value of phi, and then look at the slight differences between the sign changes. But I don't want to dwell on this because this is one that's a little bit, I think, is a little bit more confusing to follow. I'm going to try to show you another set of math on the next page and then do some drawing of pictures to try to also help the math shore up in your mind. So for starters, we have a terminology called the principal alias, and the principal alias is, on the positive frequency axis, is anything that lies on the interval 0 to pi. So if you remember the picture that from the handout last Friday, we had this aliasing strip, remember, that I handed this out? And if you want the colored version, it's on the website. If you want to print a colored one on your own, this is just what I created. So this axis that ran along on top of here, that was F running along there. But then if I divide F by Fs and multiply times 2 pi, then the axes I'm going to get would be omega hat. So I've got another version of this same plot in the notes that's in terms of omega hat, but this one is in terms of F. But it's got notated on here that this point right here is Fs over 2. So if I take Fs over 2, multiply by 2 pi, and divide by Fs, that's pi. So that's consistent with what we were just saying on the omega hat axis, that the principal alias range is from 0 to pi. I just wanted to jump over to this for a second to just let you know that that principal alias range in Hertz, being Fs over 2, corresponds to pi in terms of omega hat. Okay, in terms of the continuous time frequency, omega naught, there's no hat on here right now. The aliased frequencies are omega naught plus 2 pi L Fs, or in terms of Hertz, which is my preferred way of thinking, F naught plus L times Fs, or L times Fs minus F naught. So these three groupings in here, actually, if I was to try to put circles around them, F naught and F naught plus LFS and LFS minus F naught are all one and the same when it comes to aliasing. They all produce the exact same sequence values if we were sampling the sinusoid at frequency F naught Hertz with a sampling rate of Fs samples per second. Or boiling that down to the cosine form, like on the previous page where there's an arbitrary phase thrown in there, it works out to being that the F naught frequency sinusoid is equivalent to the F naught plus LFS with the plus phi thrown in there, or if the equivalent frequency is the LFS minus F naught, then the samples will be equivalent if we take into account the minus phi value. Right now, this plus and minus phi thing, if I was you, I'd be saying, I don't see where that's coming from, but I'm going to show you that in an example. That's actually kind of a minor point, but it's to make the math be absolutely precise, you got to do it that way. Instead, I'm going to take a simple example. For starters, I'm going to say we've got analog signal at 60 hertz, 340, and 460, and we're going to sample at 400 samples per second. And I've got the signal set up so that the 60 and 460 are at plus pi over 3, and the 340 is at minus pi over 3. So these three sinusoids fit equation 414 to a T. So I'm going to get an exact equality. The samples will perfectly match up because I've got the phases set properly to handle the negative case. But I go ahead and plot those out in MATLAB. I plot the continuous time sinusoid in blue using plot, and then I overlay on top of that using the stem function with green stems what the sample values look like. And you'll notice that the green sample values are identical in all three cases. The 60 hertz waveform is the one that's got the longest period or the lowest frequency, so it appears to have, the best representation in terms of the number of samples per cycle. The 340 hertz signal, you can see that you're getting less than 2 samples per cycle. If you just look at the cycles of the blue waveform, you're seeing less than 2. And then the last one, the 460, is the same way. But what do you see, or what do your eyes see in terms of how to connect the green dots together? Do you notice something? And how those green dots would connect together if you were just visualizing them? How do they connect together? Which signal do they appear to better represent when you connect them together just in your mind's eye? The 60 hertz. That's the aliasing concept visually there, seeing how the samples are identical. They were taken of different signals, the 60 hertz, 340, and 460, but because the sampling rate is not high enough on the 340 and the 460, the samples end up looking identical to the samples from the 60 hertz signal. Is that a crime? I mean, I'm saying that facetiously. It's like you're an imposter. You're not real anymore because you now look like something else. Okay.
So the principal alias would be lower than 60 hertz.
Well, let's check it out. The principal alias in terms of the omega hat axis has to lie on the interval 0 to pi. In terms of the hertz axis, it just has to lie between 0 and fs over 2. So is f between 0 and 400 over 2, which is 0 and 200, or is omega hat between 0 and pi? We can say for the 60 hertz that's true, right? 60 is less than 200. What does 60 hertz become in the omega hat axis? We went through this before, but it'd be 60 over 400 times 2 pi is the omega hat. And that was, let's see, scratching out these guys. 2 goes away, and that becomes a 20. So that's 6 over 20, or is it 3 over 10 times pi? I did that right? Yeah. So that works too, right? So that is the principal alias. There's no lower frequency that's the principal alias in this case to be equivalent for the 60 to be equivalent to all the others. So what I'm going to do is I'm going to go sort of off sheet here. See if I can remember how I create a blank sheet in this tool. Probably right here. The way we can see this best is on the frequency axes. and we're going to be developing this more as we go along, but if we had 0, we're sampling at 400, let's just put some other frequencies up here. Oops. So I'm thinking of the line spectra idea right now, so this is F in hertz. 60 hertz is what we started with. Now, where do the aliases lie that we just discovered relative to the 400 hertz sampling rate? The principal alias was at 60. What were the other two frequencies that we had? It was 340, right? So we had one right here. I guess I didn't draw that. Well, I guess it's good enough. And then that one was where? 460. So does anybody see the pattern or a pattern? That folded sheet of paper idea that I went through on Friday definitely confirms this, but just getting down to the math, we're wanting to show that if we had an F naught, we want to show is that equivalent to some other F1 plus and minus Fs absolute value. That's, put a K times Fs in here. When will those be equal? In other words, what can we add and subtract from Fs and still get F naught? So in this case, the way we see that is by looking at everything with respect to Fs or another multiple of Fs. So it's the key here is that this lies 60 hertz below Fs, so that makes it alias, or it lies 60 hertz above Fs. So that makes it an alias. That means that it's equivalent to the 60 hertz because it'll lie, 340 is below 400 by Fs and 460 is above Fs by 60. So what are two other aliases that you could point out the way I've got the picture drawn? It's this same equation down here. Just putting in K is equal to 2. So what would be another pair of aliases? Or did I just lose everybody?
No, I understand what you're saying, but so 2 times the frequency sample rate would be 800. But does the principal alias also get multiplied to make it work?
No, the principal, this would be, this guy right here is like that.
Okay.
And 460 is that. So now we're looking for yet another possibility that can go into there in place of F1. We might call that F1 and F2 is what we found. Suppose this is F naught. This would be like an F1 and this is an F2. They're all equivalent frequencies with regards to the 400 hertz sampling rate. So now for a different value of K, now I can find another pair of frequencies, say F3 and F4, right? That will be above and below, say 2 times Fs. See what I'm getting at? So you said 740? Yep. That's absolutely correct. I mean, that's the folding idea, and that's exactly it's exactly what this strip over here was showing. If I scratch things off of here and I said, okay, we'll put in the numbers that we have here. This was 200, and this point back in the corner is 400. So we initially were sitting over here at 60. And we came across and we said, okay, that bops down to 340, and the frequency above the 400 is the 460. And then we come all the way across over here, and now we're above and below 2 Fs by the 60, and that was the 740 and 860. Just another way of looking at the same thing. I like pictures better. Pictures, to me, are kind of a saving grace a lot of times. If you can draw a picture and prove it to yourself beyond reasonable doubt, your confidence. If you're more math-oriented, the math is definitely the way to go. And that would be this guy right in here. Searching out values of f1 such that at integer multiples of fs, I can hit this same f naught. So if I said, suppose I give you fs is equal to 1,000 hertz, and I give you an f naught of 250 hertz, and I said, first the question I might say is, what is the principal, is 250 hertz a principal alias relative to 1,000 hertz? And your answer would be, what's the test? Well, principal aliases in terms of the frequency axis in hertz have to lie between 0 and fs over 2, remember? So 250 is less than 500, so it fits. Now, what are some other frequencies with regards to a 1,000 hertz sampling rate alias to 250? And now you would go with the idea of 250 above or below 1,000, 250 above and below 2,000, and so on. Is everybody getting that? Me, I've studied this for a long time, but in trying to explain this, I sit in my office and say, they're not going to get it if I take this pure math approach because it seems so somewhat abstracted to just write down this formula right here. So I like to think of it in terms of the picture right here by saying that if it's at 340, if it's 60 hertz below 400 or 60 hertz above, or in this example here, if it's 250 hertz below 1,000, that'll alias down to 250, or if it's 250 above 1,000, that will alias to 250. So in this case, the alias frequencies would be 750, 1250, let's see, what's the next one up? Yeah, 1750 and things like that. The folding frequency is not what you use in your calculation, and that I want to point out. You don't see in this equation with the absolute value signs where I've got fs over 2 entering in there. The folding frequency, the notion of that comes about as that's what things pivot with respect to. And if I was to take this plot right here, and if I was to think, how does the folding frequency enter in? It's basically that if I take and put a fold right along here, and was to fold the drawing right along that line, what would happen is this 340 would land right on top of that 60, right? And then if I was to do an accordion deal where I would take and once I folded the sheet of paper, the 400 would be at 0, and then I folded it back in the opposite direction about the next alias folding frequency, which I guess is 600. Then it would, then this guy would land at 60 again. And then we'd basically be constructing this drawing right here, which is supposed to be like a sheet of, I don't know if you get the 3D idea with the shading. This is my artistry with, that's a sheet of paper kind of standing on the desk, and I folded it like an accordion and basically folded the frequency axis up to see how all the points correspond. This is one angle. There's a student that walked out of here just after I started lecturing, and he's come into my office saying, people, in general, he says, people try to explain this only one approach, and then those of us that don't get it are stuck. We need all these different angles, and I agree. But this is probably my favorite one. but the math one is always there at your disposal. So if you can't see this one right now, you're going to have to rely on the math expression here. And if that fails, this is always available too. You just go into MATLAB and just plug in numbers. It's kind of challenging to brute force this out though. Try all these different numbers. When will I finally get the samples to agree? I know there's something in there. So the math is probably the second easiest, or maybe it's just what you want to fall back on and you want to use the picture to kind of reinforce what the math is doing. But probably what I do when I'm confronted with a problem is I will draw a picture like this, and I will draw the frequencies out. So let's take another type of example here since I'm talking like that. Let's just clear the slate and kind of start all over again. So suppose I have a spectral line and understand that I'm doing everything in hertz, but I can always get this related back to omega hat by just taking 2 pi times f over fs. So if you wanted to work in radians per sample, you could do it that way. As a matter of fact, I'll convert it to that axis when I get done here. Suppose I'm giving a frequency at 1900 hertz, and then you're told that fs equals 600 hertz. This could be Friday's quiz. This is an example. I'm just thinking off the top of my head, looking at your expressions, just thinking how we could do this. Okay, so fs equals 600 hertz. We have a sinusoid at 1900 hertz. First question might be, what's the principal alias of 1900 hertz relative to the 600 hertz sampling rate? This is kind of a challenging problem because you have to think about this accordion and how it's all going to fold up. So you got to think in terms of math. You have to think, okay, I want to find some f naught that lies between 0 and what? Well, and the omega hat, but I'm working in hertz now. I'm going to draw the pi axis below it. But if fs is 600 hertz, what's the principal alias band that I have to have the signal lie in? 0 to 300, right? So I'd have to put a 300 over here. And then I know that my sampling rate is at 600. So I'm looking for a signal that lies in this interval right here. That's the principal alias band. So 1900 definitely isn't it. Where does the principal alias of that 1900 lie in that 0 to 300 hertz band? So I kind of have to go searching for it. But you can do it mathematically or you can do it graphically. A good way to do it graphically would be to start putting out where all these multiples occur. So we have multiples of fs, because remember everything is with respect to plus and minus a multiple of fs. So we've got 2fs. Where's 3fs going to lie at? Is that right? No, 3fs lies at 1800. I didn't draw this to scale, so I got to scratch it and start over again. Do a little bit better at least. Still kind of crunched up, but so 600, 1200, and 1800, and then 4 times fs is 2400, right? So now that I've kind of painted the picture in there of where those critical points are, can you see better how we're going to how this is going to work out. The principal alias has to be a number that lies between 0 and 300. That means we're looking to relate 1900 to either 600, 1200, 1800, or 2400 such that the difference between those two frequencies is between 0 and 300. So 1900 lies closer to 1800 or 2400? 1800. And what's the delta between those two? So is that the principal alias?
Yes.
Is everybody rock solid on that? It doesn't lie. And even if you did get it confused and you said, okay, relative to 2400, 1900 is, what's the delta there? 500. And then you'd say, whoops, that's outside the principal alias band, right? So it's got to be the 100. So the principal alias is down here at 100. So the quiz question could be, what's the principal alias of the 1900 relative to 600? And you come back with the 100. And then another question would be, what are some of the other frequencies that also alias to the principal alias value? So let's put some of those on the page now. Now that we know that the principal alias is at 100, what are some of the other frequencies that alias to 100? Okay. Okay, then we got then there's one in here, which is 17. I can see some of you are totally engaged on this. It's not that hard, right? But you have to be clear on it, what's going on here, so how things work into this. If all else fails, here's what you can do. But this is, sort of a MATLAB algorithm thing. You're looking to, in this case, you'd be putting in the 1900, and you'd add and subtract some k times 600, and you'd go chugging away by testing all those plus and minus values for different integer values k. And you'd be finding the hits, or you'd be finding out where that solution is until you found the value of k that gave you that solution. And I have a routine a couple pages away in the notes that does that, actually, in MATLAB.
So we found the principal alias band by FS over 2, right?
We did not use, the principal alias band was constrained on the interval 0 to fs over 2.
Okay.
So that gives us that part of the equation. That's our constraint. And then we find the possible candidate frequencies by stepping this along until we find that one that hits, and there is only going to be one that's going to lie in that interval. That's maybe something that's a little bit confusing, but when you add and subtract a multiple of 600, you can't possibly get more than one solution that's going to lie in the principal alias band.
So 1900 could alias to numerous other frequencies if you sample at different rates.
Exactly. Yeah. How are the rest of you feeling? Is it mind-boggling or okay? I think digital signal processing is here to stay. I've been teaching it for over 20 years, and it's more than ever the way of life amongst electrical engineering things. It's what makes almost all of our gadgets go today. Every music player, every cell phone, digital TV, everything is, when everybody says something's digital, but you interface to it by an analog means, either by seeing or hearing, there's digital signal processing making that possible. And that has to do with this sampling from analog, or taking samples and converting back to analog. So it is a fundamental importance. Let's see. So I'm going to keep lecturing some more. I'm going to show you a little demo here of something. why don't you take a look at this worksheet? I think after we just went through, you ought to be able to make pretty good progress on this between now and Wednesday. This basically is similar types of questions. I guess the other thing I didn't do in this example, even though I've got it pretty well crudded up, I'm going to clear some stuff off of here and just show you something else, since there was a question about omega hat. And this is very cool also, the way the math works out. And that is, I can come down here and I can draw the omega hat axis. And the omega hat axis is always going to be that at the sampling rate I have 2 pi, the folding frequency I have pi. Remember, fs over 2 corresponds to pi, how that works out. And then of course all the multiples are in here. So 1200 is 4 pi, 1800 was 6 pi, and so on. So we could have viewed everything in terms of the omega hat axis if you'd wanted to. So you could have converted all these analog frequencies to their digital radians per sample frequency and talked aliasing in the exact same way, except then the formula would have been what omega hat value is equal to some omega hat plus and minus k times omega sub s, where omega, no, that's not omega hat, that's just omega. Now it is omega s hat. Not that, but 2 pi. So we could have done it that way too. Same idea. It's just how you convert, whether you want to go to the discrete time first. I tend to like the analog frequency axis better just because I can relate to it physically better as if it's in hertz. The radians just seem to be more abstracted to me. I like the idea that I've got these harmonics of the sampling rate clock, and I think of the real sinusoidal frequencies that alias. So let's just take another quickie view at a demo. I've got a little application that I wrote that, not Mathematica or MATLAB, but this is just an example where I can keep the sampling rate at 1 sample per second, and I can vary the frequency of the sinusoid. And so if I'm at a really low frequency, I get multiple samples per cycle. I'm increasing the frequency, and as I get closer and closer to committing aliasing, in other words, if the input sinusoid should get up to what frequency? If I'm sampling at 1 sample per second, what's the maximum frequency I can put into this sampler without having an aliasing problem? 0.5 hertz. So right at 0.5 hertz for the input, what am I going to have? I'm going to have exactly 2 samples per cycle. Right now I'm right at that point. Notice I have a sample here, and then a sample down at the bottom, and then I start the next cycle. If I go faster, now I've got less than 2 samples per cycle. And from the previous picture in the notes, remember how we eventually saw how to connect the dots together in a lower frequency or alias sinusoid. You won't see that until I run the input frequency up higher. But as I run this up higher and higher, eventually you're going to be able to see, I get it up closer to the 1 hertz level. Now you're starting to see more clearly that there's a lower frequency sinusoid connecting these dots. And if I go further and further, see, it's even more obvious, right? That's because it folds with respect to that folding frequency. So as I get closer to 1 hertz with the input, now I'm closer to 0 hertz at the alias frequency. And when I'm right here in the middle, it's harder to see because it's at a higher frequency. I have a little button here where I can just have it display the alias frequency. So here's the input, and when I get up to that folding frequency point, the fundamental or principal alias is now what I'm going to display. Now it will, see right at that point, now it starts to go back down again, because now I'm actually having it plot the principal alias. There's a GUI in MATLAB that you're going to use on the next lab that will reinforce more of this. You're going to have another MATLAB GUI with spectra and waveform plots. So sampling theory is going to keep banging on your brain to get it in there for yet another lab. One little thing I want to show you that's pretty intriguing, and some people might argue that the sampling theory seems amazing, but the sampling theory says you have to sample at greater than twice the highest frequency. And here's the intrigue factor. If I set this right at the sampling or the folding frequency, so I'm getting 2 samples per cycle, you can say, okay, that's good enough. I have a sample at that peak, and that peak. I can reconstruct from those samples because I have 2 samples exactly. But if I shift the phase of those samples, notice what can happen. If I get the sampling rate right and I don't quite have it right on there. Exactly 2 samples per cycle with the right phasing gets you what? Nothing. You can't reconstruct something from nothing. But if you sample at just slightly greater, in other words, bring this frequency down, then there's enough samples, and it's due to the asynchronous behavior between the sampling rate clock and the signal that over time those samples will ebb and flow across the peaks of the waveform, and you will be able to reconstruct. And I'll talk more about an example in Mathematica that kind of shows you how the reconstruction works. That'll be probably next time. Anybody have any questions? No super mathematic depth required for this chapter. So if that's a myth or reality about this class being tough, the math so far has not been exceedingly challenging, I don't think. But the concepts are challenging and they require thought.